Hello. I'm going to continue talking about, I'm going to continue my lectures on in nonlinear dynamics and later nonlinear control. Today I'm just going to briefly I'm going to start talking about fundamentals of stability. I'm going to talk about other types of stabilities later. This one is Lyapunov stability, and then we're going to talk about asymptotic stability. And once we have all the stability defined, we can start talking about how we can determine different types of stability. All right, so, and also remember that when I say stability here, I'm talking about global stability versus the stability of the limit cycles, because what later we're going to talk about is that if a dynamic system has an isolated solution called the limit cycle that I briefly explained in previous lectures, then that system, that limit cycle could be stable or unstable. But right now I'm talking about the concept of stability as in global stability of dynamic systems. So Lyapunov stability, if you remember, we said that we have to remember that we have two types of systems. We have maps, discrete systems, and we have continuous systems. For both of them, we can define Lyapunov stability. Obviously, they're very similar. For example, for maps, we say that given epsilon being a small number larger than 0, there is always a delta, which is a function of epsilon, which is also larger than 0, such that if for a pair of solutions at iteration k equal m, the distance between the two solutions is less than delta, then the distance between the two solutions for k larger than m will be less than epsilon. Let me also go through the definition for continuous systems and then explain it further. For continuous systems, either non-autonomous systems or autonomous systems, we can again say for a given epsilon larger than 0, there is a delta function of epsilon larger than 0. If it was a non-autonomous system, delta is also a function of t0, such that for u minus v, u and v being the solutions of the system, dynamic system, in other words, they satisfy our dynamic system, our differential equation. U minus v is less than delta satisfies that u minus v being less than epsilon for any time larger than t equal to t0. So if at time t equal to t0 we had the distance between the two solutions less than delta, it satisfies this relationship between the two solutions when the time grows. Now let's discuss both of them further. So essentially what we are saying is that if we had the two solutions where one of them was in the neighborhood of the other, because these numbers are small. If one of them was in the neighborhood of the other one, as the time grows or as the iteration grows for discrete maps, the two solutions, one initiated from point U and the other one from U and the other one from V, the two solutions still stay in a small neighborhood of each other. And if this was the case, then we say that the dynamic system is stable in Lyapunov sense. For example, if I have this system, this is essentially a system with a cubic nonlinearity. So I describe the system in a standard form. x1 dot is x2 and x2 dot is described by this right hand side. If I ask you to determine the stability of equilibrium points, the first step is to determine the equilibrium points. Equilibrium points are the points where the right hand side of this dynamic system goes to 0, or the left hand side goes to 0. So if x1 dot goes to 0 simultaneously as x2 dot going to 0, then it means that if you're at a point x1 and x2, you're going to stay in that point for the rest of the time. That's why it's called an equilibrium point. So I'm setting the first equation equal to 0, x1 dot equal to x2 equal to 0. This obviously requires that for any equilibrium point, x2 should be 0. And then I set x2 dot equal to 0. And because x2 was 0, then we simply end up having minus x1 plus x1 cube equal to 0. Agreed? So I have this one going to 0 for our equilibrium point. Therefore, this term, the sum of these two terms should go to 0. Factor out x1 and you get x1 in open bracket minus 1 plus x1 squared equal to 0. So we have three equilibrium points, 0, 0, minus 1, 0, and 1, 0. So if I ask you to determine the stability of each of the equilibrium points in Lyapunov sense, you need to investigate what happens if you choose a V close to of any of these points as time grows. So U is my equilibrium point, and then V is the other point I choose nearby. And then I investigate if V stays in a neighborhood close to U as time grows or not. So once we have the equilibrium points, we can choose points, initial conditions, for example, near each equilibrium point. So the V's near each equilibrium points. Integrate the system for long term and test if it satisfies the condition for Lyapunov stability. For instance, then you can do the rest of it yourself. For instance, near 1, 0, I can choose 1.1 and minus 0.1. This is my point V. I can call this x10, x20. Let's call this also V0. And then I simply start numerically integrate this system. So I have my initial condition, simply use Runge-Kutta force order, and then find for a long time, integrate the system and see what you get for x1 and x2. And if you do that, you'll see that x1 and x2 for this initial condition are not bounded and grow indefinitely. Therefore, not as stable. The dynamic system would be not as stable in Lyapunov sense. I'm not going to discuss how to integrate this numerically. This is an undergrad problem. Once you integrate this, you're going to see that, or no matter how much your T grows, your solution also grows indefinitely. In other words, we cannot find a small neighborhood of the equilibrium point, this equilibrium point 1, 0, such that the motion remains confined in another small neighborhood, let's say characterized by epsilon. Right? All right. So thanks for paying attention. If you have any questions, I have my email address on About page. Email me your questions. And then next time I'm going to talk about asymptotic stability.